So I'm gonna work in three different problems similar to those ones that you are gonna find in the midterm on this Thursday. So I'm gonna solve them here, giving some ideas of how to work on them. Please email me or if you have any questions regarding the solution of these three problems. So on problem one, we have a source, and I'm gonna draw it here, a source with a peak voltage of 10 volts, and this source is connected to a source impedance that is going to be 50 ohm, and this source is connected to three different transmission lines with different lengths. So first we're going to have a quarter wavelength transmission line with characteristic impedance ECE420, 50 ohm. That's going to be followed by another transmission line with a length of half a wavelength, characteristic impedance 80 ohm. And finally, this also is going to be connected to another transmission line with characteristic impedance 100 ohm. So the first thing that we are asked is for the reflection coefficient that the generator or the source is seeing, this gamma n. So in these kind of problems, we're going to be working starting on the right, like as always, from the load. And in our case, the load is the last transmission line, right? So when we are looking at this point, we're looking right, the impedance that we see, we're going to call this C1, it's going to be equal to 100 ohm, right? The characteristic impedance of the last transmission line. So now we are adding a half a wavelength transmission line of characteristic impedance 80 ohm. So we're looking for the impedance that we have at this point, and I'm going to call it C2. In this case, the characteristic impedance is 80 ohms, but in reality, it doesn't matter what's the characteristic impedance of this transmission line. As long as we know that the length is half a wavelength, we know that on the Smith chart, we're going to travel all around the Smith chart, and we're going to end up at the same point where we started. So we know that C2, the impedance that we see here, it's going to be equal to the impedance that we have at the end of that half a wavelength transmission line. So it's equal to C1, it's going to be equal to 100 ohm. All right, so from C2, we're going to calculate what's the impedance at the input, Cin. Now we have a quarter wavelength transformer, and we know that when we have a quarter wavelength transmission line, the input impedance, it's going to be equal to the characteristic impedance of the transmission line square over the impedance that we have at the load, right at the end of that quarter wavelength transformer, in this case C2, over C2. So the input impedance is going to be equal to 50 squared over 100 equal to 25 ohm. All right, so once we have this impedance, we can calculate the reflection coefficient. And the reflection coefficient expression, it's going to be Cin minus Cs over Cin plus Cs. Of course, Cs is the impedance of the source, is the 50 ohm impedance that we have here. So we can plug in the values. It's going to be 25 minus 50 over 25 minus 50. All right. When we calculate this, we're going to have a reflection coefficient of minus 1/3. That's part A of this problem. Part B, we are asked for the power reflection coefficient. And we know that the power reflection coefficient is nothing but the magnitude of reflection coefficient squared, right? The reflection coefficient that we calculated in A is in voltage. It's expressed as a relationship between the voltage wave that is reflected to the voltage that is incident into the load. So we get the magnitude square, and that's going to be 1/9. So what that means is 1/9 of the power that is incident into this network, it's going to be reflected back. All right, part C is asking for the power delivered to the network. So in this case, what we can do is we can draw the equivalent circuit that we calculated, where we have a source, voltage source, then we have the source impedance, and then connected here, we're going to have the impedance that we just calculated, C in. Okay, this is CS, which is 50 ohm. And this C in is going to be 25 ohm. And the voltage, it's equal to 10 volts. 10 volts. Here. So in order to calculate the power that this delivered to the network is the power that is delivered to this impedance, right? C in. So we can calculate the voltage at this point. And that voltage is going to be equal to Vg times C in over C in plus Cs. It's just a voltage divider, right? And if we plug in the numbers, we're going to get a voltage of 3.33 volts. That's the voltage at this point. So with that voltage, we can calculate the power is being dissipated into this load, right? And that would be P in, it's going to be equal to 1/2 V in magnitude square over C. This 1/2, of course, accounts for transforming the peak voltage into the RMS voltage, right? It's going to be divided the voltage by the square root of 2. Since it's squared, it's going to be 1/2 when we take it out. So in this case, we're going to have 1/2 of 3.33 squared divided by 25 ohm, which is equal to 0.22 watts. All right, so that's problem 1. Now problem 2. Problem 2, we are given a series of Smith charts, and we are asked to sketch the simplest equivalent circuit topology using lumped elements. So first Smith chart that we have is this Smith chart. Right. And we are given this response of a circuit. This curve. So what that means is that the circuit was measured at different frequencies, and this is the response at different frequencies that our circuit got. And we are asked to draw what's the equivalent circuit we using lumped elements, resistors, inductors, and capacitors that will give us this response. Right? So first we need to see or to find that this curve is part of a constant conductance circle, right? So that means that the elements are going to be in parallel to each other, right? So we're going to have for sure, this is a constant conductance, so there's going to be a resistor in parallel. It's a resistor in parallel to another component. What that other component is since this is at the top half of the Smith chart, we know that this half is inductive. So that means that the component that is in parallel to the resistor is going to be an inductor. So we're going to have something like this. So this will be the equivalent circuit that gives us this response, right? We can look at what the value of R is here, right? Or what the value of G, in fact, is here. So G is going to be, since it's to the left of the center of the Smith chart, we know that the G is going to be bigger than 1. Might be something like 1.1 maybe. So that's the conductance. And that's related to this resistor, right? And then what I said, since we are at the top half, we have an inductor. Of course, as one frequency, we're going to have a one extreme of the frequency range, we're going to have one value. And the other frequency, as we're increasing or decreasing the frequency, we're going to have tend to the other value. But this is all you're asked for in a problem like this. Yes, based on what's plotted on the Smith chart, what will be the equivalent circuit? So that's the first part of the problem. There are going to be more than one Smith charts responses. So another one, for example, I'm going to give you is something like this. You're going to have a Smith chart. And we have something like this. All right. So in this case, it's different from the previous one, right? Because now we can see that the response lies right on top of a circle of constant resistance. So that means, of course, that the elements that are going to form the equivalent circuit here are going to be in series. So we're going to have a resistor, right? And then same thing as before, since we are in the top half of the Smith chart, that means that it's inductive response. So we are going to have an inductor in series with that resistor. And that's the equivalent circuit that we're asked for. Another example would be part C. We're going to have another Smith chart. And in this case, we're going to have something different. In this case, the response that we're getting is going to be something like this. So again, now we see that the response is within a constant conductance circle, apart from my poor drawing. But if this ends up being in the exam, it's going to be like more accurate response plots. But now we see that the response lies within a constant conductance circle. So again, there are going to be shunt elements. They're going to be in parallel. We're going to have, of course, a resistor that in parallel is giving us a conductance, right? But now we see that the response is partly in the top half of the Smith chart and in part in the bottom half of the Smith chart. So what this is telling us that at some frequencies, the response of our circuit is going to be inductive, and at some other frequencies, the response is going to be capacitive. So what we have is that we have a capacitor in shunt with our resistor, as well as an inductor. We know that the admittance of the inductor is going to be 1 over J omega L. The admittance of the capacitor is going to be J omega C. So if we take a lower frequencies, omega is going to be small. So that means that the capacitor admittance is going to be small and the inductor admittance is going to be large. So at lower frequencies, the response is inductive. So we are at the top of this curve response. As we increase the frequency, the inductor admittance, it's going to decrease. and the capacitor admittance is going to increase. So the circuit, it becomes more and more capacitive. So we are moving to the bottom of the response curve. So that's why we are at both sides of the Smith chart. Of course, there's going to be a frequency right here where both admittances are going to cancel each other. It's going to be at this point, right? There's going to be a resonant frequency where the admittance of the inductor and the admittance of the capacitor are going to have the same magnitude but different opposite sign. So they're going to cancel each other, and then the circuit is going to be purely resistive, right? There's going to be just here like a passive resistance. That's going to be the response of our circuit. But that's it. So one extra part of a problem like this will be asking for the values of the elements that form the equivalent circuit. So if we take part B, we saw that in part B, the circuit that is giving us the response is going to be a series resistor and inductor. But then in this part, we are told that at frequency of 1 gigahertz, F equals 1 gigahertz, the response of our equivalent circuit is this point, right at the bottom of the curve here. And at that point, we are told that the impedance, the normalized impedance, let's call it CL, normalized, it's going to be equal to 0.1, that's the conductance, and that's the resistance, because we are in a constant resistance circle and we are working with impedances. So this is the resistance, and the reactance, it's going to be plus J 0.1. We are asked for the values of the two elements, the resistor and the inductor, at that frequency 1 gigahertz, if we are reading this on the Smith chart, this value of the normalized impedance. So we can calculate that with a normalizing first. So CL, it's going to be equal to the normalized value times C naught. We haven't been told what C naught is, so we're assuming it's 50 ohm. So we have 5 plus J 5 ohm. So immediately from here, we know that the value of the resistor R is going to be 5 ohm. And for the inductor, we know that the inductance, the inductor impedance, it's going to be J omega L, and that's going to be equal to J 5 ohms. So we can take this out and have that the inductance, it's going to be equal to 5 over the frequency in radians. So that's going to be equal to 5 over 2 times pi times 1 gigahertz 10 to the 9. That's going to give us a value of 7.95 times 10 to the minus 10 henries, or we can give it as 0.8 nano henries. All right, so that's problem 2. In problem 3, we have the following circuit. So we're going to have a transmission line of a given length. In our case, the length of this transmission line, it's going to be 0.26 lambda, and characteristic impedance 75 ohm. And it's going to be terminated with a load CL equal to 150 plus J 150 ohm. And then we're asked that using a Smith chart, we should find different values. First one, it's going to be the load reflection coefficient, gamma L. So that's the reflection coefficient at the load reference plane. So this is gamma L. So in order to do that, what we're going to do is we're going to take the load impedance, we're going to normalize it. So normalized impedance is going to be the load impedance divided by the characteristic impedance, which is 75 ohms. So we're going to have 2 plus J2. That's the normalized impedance. And then we're going to go to a Smith chart and we're going to locate it. So we have here the circle of constant resistance equal 2, and this is the curve of constant reactance equals 2. Of course, the reactance is positive, so that means it's an inductive reactance, so we're at the top half of the Smith chart. So this is the load impedance, CL, normalized. All right, so we need to, from CL, we need to get the reflection coefficient on the Smith chart. So what we're going to do is, first we're going to trace a line from the center of the Smith chart, going over the load. And up here, on this scale, here we have the angle of reflection coefficient in degrees. And we can see here that the value is 30 degrees. So the angle of the reflection coefficient is going to be 30 degrees. And in order to get the magnitude, we're going to measure on the Smith chart from the center to the point where our load is, and I'm measuring 4.8 centimeters. And then that measurements, we're going to bring it to the scale here at the bottom of the Smith chart. And you can see here we have the reflection coefficient for E or I, which means for voltage or current. And we're going to start at the center and we're going to measure the same distance that we measured on the Smith chart. And then we're going to read in this scale what the reflection coefficient magnitude is. So we have 4.8, so it's at this point. And this corresponds to a magnitude of 0.62. So our reflection coefficient gamma L, it's going to be equal to 0.62 with an angle of 30 degrees. And that's what I'm going to put on our results here. So we have gamma L equal to 0.62 with an angle of 30 degrees. So that's part A. Now in part B, we are asked for the voltage stand wave ratio. And that can be found really easily on the Smith chart. We just need to go again to the scale that we were looking at here at the bottom. And you can see that all these scales start at the same point at the center. And we have the reflection coefficient. And the scale at the very top is the stand wave ratio. So we only need to trace a vertical line starting at our measurement of reflection coefficient magnitude. And we're going to read up here what the stand wave ratio is. In this case, it's about 4.25. So 4.25. That's what we're going to bring to our results. 4.25. All right. Part 3, part C, asks for what's the input impedance. So in our transmission line, what impedance we are seeing at this interface. This is going to be C in and C in. That's what we are asked for, C in. So we can go back to our Smith chart. We have CL, and we know that our transmission line is 0.26 lambda long. So we just need to read where we start this point here in wavelengths. So remember, we're going to have wavelengths towards generators. This is the scale that we are using. And the value here is, we're going to start here, and the value is 0.2 0.208 lambda, 0.208. And then we're going to add plus 0.26 lambda, that's the transmission line. So we're going to end up at 0.468. So 0.468 is where we're going to end up, 468 lambda. So we go all the way around the Smith chart looking for that value, 468, and down here we have 0.46, and 0.468 is going to be down here. So here's where we are going to go with our transmission line, right? All the way around the Smith chart to that point. All right, so now we trace a line from the center of the Smith chart to this point. And we need to measure the same magnitude of the reflection coefficient. So we measured a distance of 4.8 centimeters here. So we need to measure 4.8 centimeters here. It's going to be right here. So here's where we have our impedance C in normalized. Right? So we're going to read the values, and we have approximately 0.24 is the real part, 0.24. And then the imaginary part is about almost 0.2, 0.19. Let's say minus J 0.19. And it's negative because it's the impedance at the bottom side of the Smith chart, so that means capacitive, so it's a negative reactance. All right, so we can bring that here to our results, and the normalized input impedance, we say it's 0.24 minus J 0.19. And of course, to normalize, we just multiply by the characteristic impedance C naught. So I'm not going to do this calculation, but in the exam, if you are asked to do something like this, you should do the calculations and give the result in ohms. All right, so now we're going for D. In part D, we are asked for the distance from the load plane to the first voltage maximum in wavelengths. So we have our load reference plane, and we're going to have a standing wave here on the transmission line, and we're going to have maximums of voltage and minimums. And we are asked for that maximum. So if you remember in this point, when we are on the Smith chart and we have a load and we have a transmission line, we are rotating around the center of the Smith chart, right? And when we are rotating around there, if you remember, we are crossing the horizontal axis at some point here at the right of the origin and some point at the left. These 2 points correspond to the impedance purely real, right? There is no imaginary part for the impedance if we are at this point. So what we have here is maximum impedance, and also the voltage is going to be maximum at this point. So the points of maximum voltage are when we cross the horizontal axis on the right side of the center of the Smith chart, and the minimum voltages are when we are crossing the purely real axis on the left side of the center of the Smith chart, right? So in this case, we are asked for what's the distance from the load reference plane to where the maximum voltage, the first maximum voltage is happening. So we're going to end up here. So what we do is we trace a line from the center of the Smith chart going through that point, right? It's going to be just the horizontal axis. So it's here. And what we're going to do is we're going to measure in wavelengths this distance, right, from where our load reference plane is to that point. So this distance is the distance that we have from the load to the first maximum in voltage on the transmission line. So again, here we start at 0.208 wavelength, 208 lambda, and at this point we know that this is a quarter wavelength, so here is 0.25 lambda. Right, so this distance is going to be equal to 0.25 lambda minus 0.208 lambda. And we can put that in our results. So that length to the maximum voltage, it's going to be equal to 0.25 lambda minus our starting point, which was 0.208 lambda. So that's going to be equal to 0.042 lambda. So this is the distance where the maximum occurs. So if we go to our transmission line, we're going to have this distance at this point. If this is 0.042 lambda, here is where we have the maximum voltage. Okay, at this place, at this location of the transmission line. Alright, so finally we are asked in part E to design a matching network using a shunt stub of minimum length. So going back to our circuit, we have our load with our transmission line, and the idea is that we can place a shunt stub at some point along the transmission line. And I'm drawing it as a short-circuited stub, but it could be an open-circuited stub depending on what we need. We're going to terminate it with an open or a short. But the idea is that at some point, we can find a point where we can put this stub and then do a matching. Match this load to 75 ohm impedance, right? Like if our input impedance would be 75 ohm. So we can really easily see that on the Smith chart. So we saw here that we have our load, we have the transmission line, so we are going around the center of the Smith chart. And if we want to match with a shunt element, it doesn't matter if it's a stub or if it's an inductor or a capacitor, what we need to do is we need to intersect this circle, right? The circle where the constant conductance is equal to 1. Because if we add in the transmission line of a given length, we intersect it. Now once we're here, we can add a shunt, in this case an inductor, to go to the center of the Smith chart. Or if we have a longer transmission line and we intercept it here at the top, we can add a shunt capacitor to go to the center of the Smith chart. In our case, since our transmission line's length that we were given, this transmission line is 0.26 lambda, so we can only go from where our load is to where C in was, right? So we cannot go to this top of the Smith chart because now we don't know if we can add more transmission line or not. The only thing we know is that we have this length of transmission line. We don't know if we can add more transmission line here or not. So with the information we're being given, we need to understand that we have to put our stub or our shunt element within this distance. So again, we cannot go all the way up here, so the only solution that we have is going to be down here, right? So first of all, we need to figure out what's the length of the transmission line where we have to put the shunt stub or the shunt element, right? So what we do is we start where our load is, and we are going to end up at this point where we intercepted the constant conductance equal 1 circle. And again, I did this by hand. In the exam, you should measure this length, right? The magnitude of reflection coefficient, and then you have to measure it again here too. And in fact, I can do it because we know it's 4.8 centimeters. So if I measure 4.8 here, and we intersect it, from the center, measure 4.8, and it has to intersect the constant conductance equal 1 circle. So this is the point where we're going to have it. So it's a little lower than the one I draw by hand, but not too far. So this one here, this is where we want to end up with our transmission line. So what we do now is at that point, we trace a line from the center of the Smith chart and going through that point. All right. And now we're going to figure out what's the distance from the load where we're going to put our stub, right? So here we read that this value here is 0.42, about 0.428 lambda, 0.428 lambda. So now we start our initial point, 0.208 lambda, and we're going to end up at our point of 0.428 lambda. So this distance is going to be equal to the length of the transmission line. It's going to be equal to 0.428 lambda minus 0.208 lambda. So that's going to be equal to 0.22 lambda. All right, so this is the point, the distance from the load where we have to put our stub to perform the matching. So 0.22 lambda, we go up here, this distance, right, from the load to our stub, this has to be 0.22 lambda. All right, so now we know what the exact position where we need to put our stub, or again, in this case, stub could be like a shunt load, shunt, in this case, inductor. So, all right, we are at this point. We know that we want to end up, we're going to go from here, we're going to go to the center of the Smith chart. So what we're going to do is at this point, we're going to read the admittance, right? Since we are working with shunt elements, we want to work with admittance values. So the admittance at this point, and I'm going to call it Y1, it's normalized, it's going to be equal to, of course, the real part is going to be 1 because we are in the constant conductance equals 1 circle. So that's 1. And then the susceptance, we need to, check the blue line that goes through it, is this one. It goes down here, and the value is 1.6. So plus J 1.6. We know that we are in the bottom half of the Smith chart, it's capacitive. The admittance of a capacitor is positive, J 1.6. All right, so this is the admittance that we have here. Now what we know, if we go back to our circuit, is that at this point, if we look right, that's the admittance that we have, Y1. Y1, normalized. Now we're going to add another admittance in parallel, is the admittance of our stub. So this one, it's going to be Y stub. Right? So we are going to add these two admittances. So we are going to have Y1 plus Y of our stub. And what do we want this to be equal, right? We add the two admittances. We want to end up at the center of the Smith chart. So the admittance at the center of the Smith chart is the Y equal 1. It's a perfect match. So this has to be equal to, let's call it Y in. Well, let's just say it's 1. We don't want to, it's 1, right? The center of the Smith chart. So now we know that these two values, right? We know that Y1, we read the value here, and we know what the result value is, so we can figure out what the admittance of the stub has to be. So the admittance of the stub it's going to be equal to 1 minus the admittance y1 that we found in the Smith chart. So this is going to be equal to 1 minus, and then the admittance that we got was 1 plus j 1.6, right? So these two are going to cancel out, and then we know that the admittance of the stub that we're looking for, it's going to be equal to minus j 1.6. All right. So if we were to do this matching using a lumped element, since we know that the admittance that we want is negative, which element give us a negative admittance? That's going to be an inductor. So we could add an inductor with this admittance, and that will do the matching. It will take us from this point y1 to the center of the Smith chart. Since we want to use a stub, we need to figure out what's the length of that stub has to be in order to get that admittance of minus j 1.6. So first of all, we're going to find where this value is on the Smith chart. Minus j 1.6. We know that admittances are negative at the top, are inductive, and the of an inductor is negative. So we're going to look for 1.6 up here. And we have this curve here. It's this blue curve. Goes here is 1.6. So this point corresponds to minus j 1.6. All right. So if we're going to design this with a stub, again, we know that we can start our stub with, we can terminate our stubs with a short or an open. And we know that in the Smith chart, we have a short here. This corresponds to a short. And this point here corresponds to an open. Really high impedance, it's an open. Really small impedance, 0, it's going to be a short. So of course, if we start from a short, it's going to be a shorter, the stub is going to be shorter than if we start with an open, because we will have to travel all around the Smith chart to get to this value that we are looking for, this minus j 1.6. So this is telling us that the stub that we want to terminate our stub with a short. It's going to be a short-ended stub. So we start here, and we want to go all the way up to this point here. I'm going to that point there. So this is going to be the length of our stub, short circuit stub. Okay, and then we can read. We start at 0, wavelength of our generator, and this is going to be about 0.087 lambda. So, all right, that's the length of our stub. So we know that this is the length of our transmission line, right, that we calculated. Then we're going to put the stub, that the stub is short-circuited, so we need to mention in our results that our stub is going to be short-circuited. So we can even draw our stub. Okay, so it's short-circuited here. You can see that it's short-circuited. Characteristic impedance is C0. And then the length, we can just say here, this is going to be the length of our stub. And it's going to be equal to 0.087 lambda. That's the length of our stub. All right, so yeah, that's the idea. You will give your results, you will give your calculations, and also here on the Smith chart, you will highlight or mark what your process was, right? You have a load here, you have a transmission line to get to this point Y1, the transmission line length, you will drop here, probably you can label it down here, and then to get up there, you read the admittance, you know this value, and then to synthesize that value with an opposite sign, you need a stub, and this stub is short-circuited, so we start at the short. You can even mention here on the Smith chart this short, and then here is the length of the stub, which is equal to that value, 0.087 lambda, and that's the value that you get, the admittance that you get with your stub. And that would be it. So hopefully it's clear enough. If you have any question about any of the problems, feel free to shoot me an email, and I will try to answer any questions you may have. So thank you.